Hello, welcome back to our daily math video. Today we're asked to solve an AMC problem, AMC 12A, from the year 2019, problem number 23. Okay, so this is problem 23. We can already expect it's going to be pretty tricky. It isn't like problem 25, but it's still up there down the list. Alright, and even the problem is even pretty lengthy too, almost half a page. So let's not get intimidated and let's just get through this problem, and we'll soon see that a lot of these words are just fancy math terminology, and we can just see that it's really asking us for something pretty simple. So it's defining binary operations, diamond and heart. By a diamond b is a to the log base 7 of b, and a heart b is a to the 1 over log base 7 of b. Interesting. So the first thing we notice is that these exponents are reciprocals of each other. So that may help us simplify some things further down the problem as we get into it. And obviously for real numbers a and b, for which the expressions are defined, so that the logarithms are defined. So a and b are both positive. So now it's saying to define sequence a sub n recursively, starting with a sub 3 is 3 heart 2 with this operation over here. And then whenever we want to go to the next term, we just say a sub n is just n heart n minus 1, diamond the previous term, a sub n minus 1. And this is for all integers n is greater than or equal to 4. So in the end, it's pretty much just asking us for log base 7 of a sub 2019 to the nearest integer. Alright, okay, so first thing we notice with what it's asking us, or one of the first things, is it's using a sub 2019, which is a crazy big term in the sequence. Well, we don't know if it's actually big, but it's really far along. And that just gets me thinking, does this simplify in such a way so that we can just find a formula to find a sub 2019? Because that would be much, much easier than just plugging in over and over and over into this expression 2019 times to get a sub 2019. Alright, let's see if this is possible. Well, I'm sure it is possible, because they wouldn't put this on a math competition if it didn't simplify pretty easily. So let's just start with what they gave us. A sub 3 is 3 heart 2. So 3 heart 2 is 3 to the 1 over log base 7 of 2, because we can refer up to this formula. A heart b is a to the 1 over log base 7 of b. Alright, now we can use an important property of logarithms. We're going to be using this property many times in this video. What it is we can take the reciprocal here and switch the base of the logarithm and the argument inside the logarithm. And we can reciprocate the logarithm. And it still is the same thing. So this is just the same thing as 3 to the log base 2 of 7. So we took the reciprocal and we switched the base and the argument. So instead of log base 7 of 2, it's log base 2 of 7. Interesting. So that's our value for a sub 3. Let's see what we get for a sub 4. And with this formula here, a sub n, so a sub 4 is just 4 heart 4 minus 1, which is 4 heart 3. Diamond, the previous term, a sub 4 minus 1, which is just a sub 3. And remember, a sub 3 is just 3 to the log base 2 of 7. Alright, so 4 heart 3 is just 4 to the 1 over log base 7 of 3, applying the formula we have above here. Alright, so now we use a diamond operation. So a diamond b is just a to the log base 7 of b. We don't reciprocate it this time as we did for the heart operation. Alright, so it's the first one, 4 to the 1 over log base 7 of 3. And then the diamond, the second one. And the second one is 3 to the log base 2 of 7. So it's log base 7 of 3 to the log base 2 of 7. Because the b goes inside a log base 7. Alright, this looks pretty crazy here. You can verify this more deeply if you look and actually do the algebra manipulation here. And you can just verify with more clean intuition that this is actually the same thing as this, because it can be pretty messy. Alright, so now let's use some more logarithm identities to simplify this. Remember, we can reciprocate this and we switch the argument and the base. Again, we can do the same thing here for 1 over log base 7 of 3. It's just the same thing as 4 to the log base 3 of 7, because we switched the base and the argument inside from 7 to 3 to 3 to 7. And we can also make it the reciprocal to keep the expression the same. And once more, we use another property of logarithms where we just take the exponent out and multiply it by the logarithm in front of it. So again, we have here log base 2 of 7, because that was our exponent, times log base 7 of 3. Alright, so that's a sub 4. We can simplify this more by using the chain rule of logarithms, because log base 2 of 7 times log base 7 of 3, that's just log base 2 of 3. Because whenever we have a logarithm with the same argument as another logarithm with the same base, then we can use chain rule of logarithms to cancel these 7s, and we're just left with log base 2 of 3. Alright, almost there now. Now we just need to use exponent rules to multiply these two powers. So a sub 4 is just 4 to the log base 2 of 3 times log base 3 of 7. Once more, applying chain rule of logarithms, it's just 4 to the log base 2 of 7, because these two 3's cancel, and we're just left with 4 to the log base 2 of 7. Alright, well, I'm starting to see a pattern here that may find itself again in a sub 5. I'm not sure, but we can hypothesize that because a sub 3 is 3 to the log base 2 of 7, and a sub 4 is 4 to the log base 2 of 7, let's hypothesize a sub 5 is 5 to the log base 2 of 7. And let's see if we're right. So let's go to the algebra once more. A sub 5, using this definition, is just 5 heart 4, diamond a sub 4. And a sub 4 is just 4 to the log base 3 of 7. Or sorry, a sub 4 is just 4 to the log base 2 of 7. Sorry, I need to correct that. Alright, so let's apply this once more. The heart operation says 5 heart 4 is 5 to the 1 over log base 7 of 4. And again, the diamond operation tells you to raise the first number to the log base 7 of the second number. So to the log base 7, and the second number is just 4 to the log base 2 of 7. So 4 to the log base 2 of 7. And once more, using some algebra, chain rule of logarithms, and we can reciprocate these and change the base and the argument, we'll eventually find that a sub 5 is 5 to the log base 2 of 7. Now, if you're skeptical about this, just apply the same sort of steps as we did for a sub 4. It's almost the exact same thing, except we're just doing it for a sub 5 instead. Alright, so we seem pretty set that we can conjecture now that for any integer n is greater than or equal to 3, a sub n is just n to the log base 2 of 7. Why? Because it seemed to work for a sub 5. A sub 5 is 5 to the log base 2 of 7. A sub 4 is 4 to the log base 2 of 7. And a sub 3 is 3 to the log base 2 of 7. So why not just generalize or conjecture that a sub n is n to the log base 2 of 7 for integers n is greater than or equal to 3? So how would we prove this? Because in math, you need to prove everything. Well, first off, we can just assume that if it holds that a sub k is k to the log base 2 of 7, if this is true, then this is also true. We need to prove that this is true given a sub k is equal to k to the log base 2 of 7. Alright, so we just need to prove a sub k plus 1 also holds and is equal to k plus 1 to the log base 2 of 7. So how will this prove this? Well, if we can find a value of k such that this holds, then it'll also hold for k plus 1, right? And if it holds for k plus 1, we can set this to be k plus 1 over here. And we can show it also holds for k plus 2. And then again, because it holds for k plus 2, we can also show it holds for k plus 3. And we can continue this indefinitely. This is called induction, proof by induction in mathematics. And we can go on and on indefinitely and prove it for all integers above a certain value of k. And in this case, k is 3. We start with a sub 3. By the definition, it told us a sub 3 is 3 heart 2. And we showed before it's just 3 to the log base 2 of 7. Alright, so this satisfies our first condition. Okay, so now let's try to see and prove that given a sub k is equal to k to the log base 2 of 7, a sub k plus 1 is equal to k plus 1 to the log base 2 of 7. And if this is true, then we've proved it for all integers n is greater than or equal to 3, that a sub n is equal to n to the log base 2 of 7. Alright, so a sub k plus 1, using the formula we had before, a sub n is n heart n minus 1, diamond a sub n minus 1. So a sub k plus 1 is k plus 1 heart k plus 1 minus 1, which is just k, diamond a sub k plus 1 minus 1, which is just a sub k. Alright, so let's simplify this over here. This is just the same thing as k plus 1 to the 1 over log base 7 of k, because we use the heart operation we have defined over here. And then we still have that diamond k to the log base 2 of 7. Why? Because a sub k is just k to the log base 2 of 7 because of our assumption here. We assume a sub k is just k to the log base 2 of 7. Alright, so simplifying this, we get k plus 1 to the log base k of 7, because we can take this reciprocal rule and switch the argument in the base. And we also apply the diamond operation, and we get to the log base 7 of k to the log base 2 of 7. Alright, simplifying, we get chain rule of logarithms by taking this exponent out here. It becomes log base 2 of 7 times log base 7 of k. So that's the same thing as log base 2 of k. And then we can use an exponent rule to multiply these two powers to find that a sub k plus 1 is just k plus 1 to the log base 2 of k times log base k of 7. And again, chain rule of logarithms, which is just k plus 1 to the log base 2 of 7. And viola, we've proved it, finally proved it, that if we assume a sub k is just k to the log base 2 of 7, then a sub k plus 1 is just k plus 1 to the log base 2 of 7. Perfect. And because this holds for k is equal to 3, then we've proved it for k is equal to 4. Now, we can also equally assume that because it holds for k is equal to 4, then we can prove it holds for k is equal to 5. Because it holds for k equals 5, we can prove it holds for k equals 6. And so on and so forth. We can prove it indefinitely for all integers, such that a sub n is equal to n to the log base 2 of 7 for all integers n is greater than or equal to 3. So now that we've proved that rigorously, we can now apply this formula without any fear that we're wrong. So, let's find a sub 2019, because remember, we can't forget that our problem is asking us to find log base 7 of a sub 2019. So a sub 2019, by our formula here, a sub 2019 is 2019 to the log base 2 of 7. Alright, so it's asking us to find log base 7 of a sub 2019. So it's log base 7 of 2019 to the log base 2 of 7. Now we can take the exponents out and multiply, and it's just the same thing as log base 2 of 7 times log base 7 of 2019. Using the chain rule of logarithms, this is just the same thing as log base 2 of 2019. Alright, and it's asking us to find it to the nearest integer. So how would we do that? Well, we need to see for powers of 2. So what are the powers of 2? Well, powers of 2 are like 512, 1024, 2048. And we need to find the power of 2 that is closest to 2019. And we can see that that's probably 2048, because that's closer than 1024, and the next power of 2 is just 4096. Alright, so because this is closest to 2048, what's log base 2 of 2048? Well, that's 11, and you can verify this computationally because 2 to the 11th power is just 2048, and that's closest to 2019. Alright, so finally, we found our answer. Our answer is 11 because log base 7 of a sub 2019 is closest to the integer 11. Now, isn't that crazy? We went through all this proof, all of this conjecturing, all of this pattern finding, and read through all of this to find that our answer to the nearest integer is just 11. Now, if you have any other faster ways or any other more creative ways for tackling this, or even just another creative way that I might have overlooked here, please comment down below and tell me what you think of this method for finding a solution. Also, if you like the video, please like it, because that will really, really tell me that you like these kind of videos, and I'll continue to make these kind of videos. And thank you for watching this video. Bye-bye.